Welcome back, everyone. In this video, I will begin the lecture for properties of derivatives, power rule, and exponential rule. Now, in this video and in this section, what we're going to be doing is start talking about what are known as the derivative rules. And what they're going to do is they're going to allow us to compute derivatives in a much easier way than using that limit definition. However, naturally, we're not going to be doing derivatives that are only as easy visually to do as the previous section. We're going to be able to do much more complicated things. Now, probably the biggest thing about derivative rules, and I wrote this on top before we even start talking about anything about derivative rules and their properties, is that when you're looking at derivative rules, they're used to help you compute derivatives naturally, but you have to take them very literally. You have to use them correct. And probably the most important thing is that when you have a derivative rule, it'll be very specific. It'll tell you you can do the derivative of this very specific thing, very specific function. If anything is thrown off about that function, which we'll talk about as we go through, then you cannot do it. And one thing is that the way our functions are written, naturally, I'm not going to ask you to do a derivative that you can't do with the rules that we will have at up to that point, but you may have to use algebraic manipulation to find the derivatives and correctly apply the derivative rules. Now, one thing that's great, one of the big things about the limits, what we talked about the entire time, is that when you're doing a limit, what's going on is that you can cancel things out until you plug it in, right? If we had 0 over 0, what we could do is factor or do some type of algebraic manipulation, cancel out, and then plug in our number. With a normal function, we just can't cancel things out because we would be changing the function, even if just by a little bit. So what we found last couple sections, is that the derivative is just a special limit. So if you need to, you can cancel, you can do whatever you need to, basically, as long as it's not breaking any algebra rules. Naturally, we can't just multiply something by 0 and make it 0 and have everything go away. But if you need to cancel, factor and cancel, do something like that to make the function follow one of your properties, you can do that. All right, so with that, I'm going to go ahead and jump into the properties of derivatives. Now, these 4 properties I have, these are typically thought of as the backbone of derivatives. These are not necessarily thought of as quote unquote rules of derivatives, because they only allow you to do very specific things. These alone will not allow us to do derivatives of many things, but they really help as far as doing derivatives when they become more challenging. And what I want to do, pretty much every derivative rule that you have, or property, whatever you want to call them, it's almost better to know what it's saying in words than a formula. Now, it's important to know the formula, of course, but really you want to know what the formula is saying in words, because they can get a little bit complicated. So the setup here says let f and g be a function which are differentiable at a number, x equals c. Now, all I'm saying here is that we can do the derivative. Okay, if it wasn't differentiable, then doing the derivative of f of x, for example, would not make sense. So we're just saying we can do the derivative, and let a be any real number. Then the basic property of derivatives are the following. The first one, called scalar multiplication, you saw that with limits, and it works with derivatives as well. What it says is if you're trying to do the derivative of a number times a function, so a times f of x, what you can do is you can bring the number outside. So visually, the way I like to look at this is that if we have just a number multiplying our function, whatever our function might be, we can bring it outside, and that's what this equation is saying. This is going to be a very important property. We can bring the numbers multiplying functions outside. Now, when you get more used to this, what you're gonna eventually recognize And think about this as more so as not necessarily bringing the numbers outside, but just leaving them alone. So if we have 3 times a function, you know that 3 is just going to sit there while you do the derivative. So the other way to think about it is number multiplying a function just stays there. It doesn't move. But once again, I'll pretty much going to follow the rules as they are, especially with the first few examples, so you can see what I mean. The way we're going to think about it in future sections is the second way, but the first way is how we really want to see it works. All right, now the second one is the addition and subtraction rule. Pretty much says that if you have to do the derivative of 2 functions and they're added or subtracted, then you do the derivative of each part with the proper addition or subtraction between them, whatever it was. So what this is saying, the way I think about this one is you can break up derivatives over addition or subtraction. Now notice we don't have a multiplication, we don't have a division. That's actually much more complicated. You can't just break it up. This is only for addition and subtraction. Also, we don't have powers. So if you're kind of comparing this to the limit laws are a very long list of properties sort of set up like this. You can pretty much do whatever you want with derivatives, scalar multiplication, addition, and subtraction. That's pretty much the only ones you can do every time. So we can break up derivatives over plus or minus. And visually, we'll see that it's going to look exactly like that when we do it. When we get more used to it, we'll think about doing the derivative of each part. That's going to be the easier way to think about it once we work through a few examples and see how it works. All right, the third and fourth properties here are just derivatives of very special functions, but because the derivative is representing the slope, we actually know how to do this from the derivative definition using the limits, but we can also use it from the graph. And we'll just use it from the graph here because we've really done these in the past section. This one says the derivative of a number equals 0. Right, a is just representing a number. It says the derivative of a number equals 0. Now, very important. This is a derivative of a number by itself. Up here in number 1, when we're talking about scalar multiplication, it's a is multiplying something with x. Okay, just very important to know how to use these rules properly is that if we're multiplying a number times x, the number just sticks around. If we have a number just by itself, the derivative of that number is 0. Now, why does that make sense? Well, it makes sense because of if you think about the graph of what just a number is, and what I'll just go ahead and do is pull up Desmos and remind you that if you graph just a number, y equals a number, let's say 4, but it can be any number. It's a horizontal line. What's the slope of a horizontal line? You should remember that it is 0. The slope of a horizontal line is 0 because the change in y is 0, and that's kind of thought of as the rise. So rise over 1 would be 0 over something, which is 0. Right. So the derivative of just a number is 0. What is the last one saying? The last one saying the derivative of the function x with respect to x is equal to 1. So this is going to be important as we go through the sections because we might have equations that have more than one letter in it. It could have x and then maybe a t or something. Whenever you write the derivative like this, do the derivative with the d and the dx, the x down here is saying what to do the derivative with respect to. So what this one is really saying is that if these two match, the derivative of just x equals 1. But I'm going to write the with respect to. This is often abbreviated WRT, with respect to, equals 1. Now, if this was a y down here and a y in here, it would still be 1. So if they're matching, it's still 1. Now, one thing I want to do as well with this one is just show it to you, because we know what y equals x looks like. That's a line with slope 1. And since a derivative really is just the slope, the derivative of this function, we can do it by the limit definition of the derivative. And we did it in some problems last time. The slope of this line is just 1. Now, one thing that's going on here, these are really so important, but also when we talk about derivative rules, they're inside one of our rules, but it doesn't really look like it. It's more useful to know these as sort of two separate rules. So remember that the derivative of just a number is 0. The derivative of just x is 1. Right. Now, when you throw all these properties together, this will actually tell you, and we'll do an example or two below, that you can find the derivative of any line. Now, because we know that derivative is just the slope and we know how to see the slope of a line, we shouldn't be surprised by our answer, but we should go ahead and do it. So I wanted to go ahead and look at a couple problems here. It says, for the following functions, compute the indicated derivative. And for the first one here, we have find f prime of x if f of x equals 3/5 times x minus 6. Now, using what we just talked about and what we know about the derivative, our answer should be 3/5. But I don't want to write it just equals 3/5 because I want you to see, using these properties, how everything works. That's really important. Okay, so when we want to do f prime of x, this is the way I like to write it. Some people like to do it a different way, but what we're saying is do the derivative of f of x. Well, anytime I want to do the derivative, I do d over, in this case, dx, because our variable is x here, and then I write my function inside. The 3/5x minus 6. This is saying exactly what the left side's saying. This side saying do the derivative of f of x. This thing is saying do the derivative of 3x minus 6, which is what f of x is. All right, now what we have to do is use our properties up here, properties 1, 2, 3, and 4, to be able to actually figure this out. Because the end goal is to get rid of the derivative symbol completely. We don't want any derivative symbols left. Once they're all gone, we are done. Well, one thing you have to notice here and take about the derivative rules is they're very literal, right? We do not have a way to just compute this all at once. Once we get more familiar with it, we'll just do it all at once and we'll know that it's 3/5. But how are we going to do it using our 4 rules up here? Well, the third and fourth rules say if we have just a number inside or just an x inside, then we know the derivative is 0 or 1. Neither of those work in this case because this is more complicated. We don't have just a number in here, but we don't have just x in here either. So it boils it down to either needing to use property 1 or 2. Pretty much the easiest thing to realize is that if you have a plus or a minus, you're going to use property 2 first. And that's exactly what we're going to do. It says do the derivative of each part. So I'm going to have the derivative of the first part, 3/5x, minus the derivative of the second part, just 6. All right, now notice you did the derivative of each part and I took the minus that was between and I just left it between the derivatives. I used exactly rule 2 here with the subtraction. Right. Now what do we want to do? Can we apply rules 3 and 4? Well, we actually can in the second one because what's the second one? We're doing the derivative of just a number, just 6. But by rule 3 here, the derivative of just 6 is 0. Now, can we apply rule 4? Because we do have an x in there, can we apply rule 4 to the first part yet? Technically, we cannot. Because like I mentioned, it has to be just x inside and we have something times x. All right, so what do we do if we're multiplying something times x? We want to get it out of there. Well, luckily for us, that's what rule 1 tells us. Rule 1 tells us we can take the number multiplying our function, which is just x, and move it out front. And when we do that, we get 3/5 times d over dx, the derivative, and now the only thing inside is x. And what can we do from here? Now we can apply our rules. The 3/5 is just a number. It's not inside the derivative, so it just sticks around. And then d over dx, that's exactly rule 4. It says the derivative of x with respect to x is just 1. And then this is minus 0. Now, obviously, we don't really keep around minus zeros, but just for the sake of finishing, we have that. And then when we simplify this, we actually just get one number. 3 over 5 times 1 is 3 over 5, minus 0 is 3 over 5. Exactly what we expected to get from the beginning because we know the derivative is the slope. But of course, not all functions are going to be lines, and that's why it's important to realize how you go through the process. Now, one thing I like to do with these examples at first is really compare them to the beginning. Okay, so why I wanted to actually leave the 3 over 5 times 1 minus 0 there is I wanted to compare it to just your function. Notice here that if I had kind of skipped some steps, right? I know with derivatives, I'm just going to leave numbers that are multiplying functions with x, so just x by themselves. So the 3 over 5 ends up staying. Wait, let me use a different color to color code this. So that 3 over 5 pretty much ends up staying. The x, what is the derivative of x? Well, that's just 1. Minus, that just stays as a minus. And then the derivative of 6, because that's a number, is just 0. And the hope is, as you do more and more of these problems, you get more comfortable with the idea that when you're doing the derivative, you're going to recognize this at the beginning. But it's very important to go through the steps first, see the process, and eventually you'll get to the point where you can start to skip steps, quote unquote, skip steps, because you're doing them in your head. All right, now number two. Number 2 is kind of a classic problem used to throw off students because they don't recognize something right away. So it says find z prime, the derivative of z, if z equals 3 to the 5th. Well, one thing is we haven't talked about exponents at all. We don't have anything about exponents here. So that should be throwing you an alarm. But what you want to recognize is 3 over 5th. This is just a number. What is it? You can type it in your calculator. But the point is, it's just a number. So when we do the derivative, we're doing d over, we don't really know the letter of our variable here. I'll just pretend it's x. When we do the derivative of 3/5, which is just a number, what's the derivative of just a number? It's 0. So the derivative of this thing is just 0. Right? And that's it. But very often, especially because of what the power rule is going to tell us, is students will see exponents and automatically try to use the power rule. And that's not the case here because it's just a number. So that's just something I wanted to kind of preview a little bit. Now I think at this point, I'll go ahead and stop since we're around 20 minutes. And in the next section, we'll pick up talking about the power rule, or the next video, still in the same section. I'll see you there.